Untreated, rabies infections are inevitably fatal. Ebola viruses kill more than 75% of the people they infect. Bubonic plague 60%, SARS about 15%, malaria maybe 1%, flu less than 0.1%. Why are some pathogens more fatal than others? A large number of factors come into play: immunity, infecting dose, host genetics, and of course medical treatment. But one answer is that some pathogens are genuinely nastier than others. This is most easily seen in animal diseases, where it is possible to experimentally infect animals with different strains and compare the outcome. I work on a disease of chickens called Marek's disease. It is caused by a virus. When it was first described in the early part of last century, it was a mild disease causing few fatalities. A strain in our collection from the 1960s kills about half of unvaccinated birds in 2 months. Our hottest strains, which come from today's commercial poultry operations, kill all unvaccinated birds in 10 days. That is a frightening statistic, but high-path bird flu is even more lethal. It kills all unvaccinated birds in 3 days. Experimental infection studies almost always find that pathogen populations contain strains which are more or less harmful to the hosts they infect. That means there is genetic variation on which natural selection can act. In other words, pathogens could evolve to be nicer or nastier. So one of the explanations for why some diseases are more nasty than others must be that evolution made them so. The question then becomes, why has natural selection favoured nasty strains in some species and nicer strains in others? What stops even nastier malaria parasites spreading in the world? Or conversely, what stops milder malaria strains spreading? A related question is this: when SARS jumped into the human population in 2002, it killed about 10% of the people it infected. If that disease had become endemic in humans, would it have evolved to kill more or fewer people? The old answer was that evolution eventually produces infectious diseases which do not harm their host. The thinking was that pathogen strains that kill the hosts also kill themselves and so become evolutionary dead ends. Nice strains come to dominate because they keep their hosts and therefore themselves alive, and so can transmit on to other hosts. Under this old theory, nasty diseases are explained as being relatively new and on their way to becoming nice. So for instance, HIV would be said to be nasty because only recently has it jumped from humans into humans from chimpanzees. Given enough time, this old thinking goes, today's HIV strains that kill will be replaced by strains that do not. We now know that this theory is wrong. Infectious diseases will not all eventually evolve to be nice. We know this for several reasons. First, we have seen diseases evolve to become nastier. Marek's disease virus in poultry that I mentioned is one example. Scientists argue about how many thousands of years people have been getting malaria, but even 1,000 years is more than enough time for nice malaria strains to replace nasty ones, and malaria still kills hundreds of thousands of people a year. The idea that pathogens always evolve to be nice is also clearly wrong in theory. Sure, in the limit, it must be true that pathogens which instantly kill its hosts will have no evolutionary future. But no diseases are at that limit. Even pretty nasty diseases can get a lot of transmission done in the process of killing the host. For example, while a person is dying from malaria, they can infect a lot of mosquitoes, which will pass the disease on to other humans. The idea that diseases evolve to be nice, that well-adapted pathogens don't kill their host, is mistaken because it assumes transmission to new hosts is maximised only if the host lives. And that just isn't true. And consider the converse. It's easy to imagine a pathogen that doesn't kill its host because it doesn't replicate well. Sure, it doesn't do the host much harm, but it also won't transmit much either. The moral of the story is that nice pathogens need not win. In the 1980s, people began to realise this, and the old idea that everything evolved to be nice got replaced by a more complicated idea. Sure, pathogens can evolve to be nice, but they can also evolve to be nasty. It all depends. This "it all depends" idea is known by biologists as the trade-off hypothesis of virulence evolution. It is basically a cost-benefit argument. You can do this in your head. Evolutionary costs and benefits are, in the infectious disease context, measured in terms of new hosts infected. Envisage strains that are more or less nasty. Which will be favoured by evolution? It will be the one which leaves more secondary cases per case. If the nice strain infects more people, it will win. If the nasty one does, it will win. That's easy to say. The next step is the hard bit. To figure out what will happen in any particular disease, you need to know a lot about the natural history of the system. So to show you how this way of thinking works, I need to focus on a single disease. I'll use malaria because it's what I've spent the last 20 years trying to understand. I want to know why malaria parasites are virulent. Malaria is a disease of human blood caused by single-celled parasites. They are transmitted between humans by mosquitoes. Now think of the evolutionary cost of virulence. Mosquitoes don't bite dead people. More virulent malaria strains will have a greater likelihood of killing the host and doing so more quickly. That means infections caused by really virulent strains will on average be infectious for less time than infections caused by nicer strains. That is the evolutionary cost of virulence, and because of that cost, natural selection will favour less virulent strains. But now think of the evolutionary benefits of virulence. In experimental work in my lab with mouse malaria, we have found that virulent strains outcompete less virulent strains, they evade immunity better, and they make more transmission stages per day. They're also better at debilitating the host, which probably makes it an easier target for mosquitoes, because a healthy person can easily swat mosquitoes, whereas a really sick person doesn't care. So virulent strains have evolutionary advantages as well as evolutionary disadvantages. Those evolutionary costs and benefits generate selection in opposing directions. The trade-off hypothesis says that the level of nastiness we see in a disease is where those costs and benefits balance out. So if you want to ask the question, why is malaria so nasty? The evolutionary answer is that strains which are nicer than those which we see in nature lose in head-to-head competition, they're more rapidly cleared by immunity, and they produce fewer transmission stages per day. If you want to ask why is malaria not even nastier, the answer is that nastier strains have shorter infectious periods because they kill their hosts. So that's how the trade-off hypothesis of virulence evolution works. How well has this hypothesis held up since it was first proposed in the 1980s? Well, it remains perhaps the key theory, but it is controversial. There are some very compelling data which support it for some diseases for sure, but those diseases are of water fleas or chickens or rabbits or mice or plants. For many diseases of humans, we don't know enough about the evolutionary costs and benefits to know if the model applies. And it certainly won't in many cases. For instance, rabies is a spillover disease in humans. It does not transmit from person to person, but rather from dog to dog or bat to bat. And we get it when a dog or a bat accidentally bites us. That means the evolutionary action is happening in dogs or bats, not humans, so the model cannot explain why it almost always kills humans. Let me finish by explaining why understanding the evolutionary forces shaping virulence is of more than academic interest. For most diseases we know of, there are virulent strains, but they are rare. Some evolutionary force is keeping those hot strains down. When we start to use vaccines or drugs or mosquito screens or sewage systems or airplanes, or when we crowd animals onto farms or ourselves into cities, when we do any of those things, we are changing the natural history of the disease system. In some cases, that might make the hot strains even rarer. But which of those things will make them more common? Diseases we control in the short term could years or decades later evolve back and bite us. We need to understand what keeps nasty strains rare so we can keep them rare.